Swayam Prabha. Digital India. Educated India.
Okay, students, last few classes I taught you the different pretreatment methods and how you can clean the surface and how this enhanced activity that we are getting after the pretreatment, it can be affected by aging effect. Now, let's use all those electrodes after the pretreatment for biosensor development. For example, I will give you one for printed circuit board like PCB. As you know, like printed circuit board that recently it has a huge impact for the biosensor development. Why? Because PCB based electrodes we can easily integrate like other stuff that we need for lab on a chip development. You can remember lab on a chip means all the lab work that we are going to bring on a single chip. So there you may need like sample processing, sample purifications, maybe sample amplification, sample delivery. So everything that's why you need some microfluidics, right? You need electronics. So everything can be definitely it can be integrated on the PCB. But if you want to use the PCB for your biosensor development, you may face some challenges. Let's show you the challenges that you may face. First of all, basically in industry level, when we are developing the PCB, we have very good fabrication facility all over the India. All the electronics, they have the printed circuit board. But the new thing, why we wanted to use the PCB? Because as the fabrication method, everything, all the procedures is well established, and we can make this printed circuit board in a large scale. And if you can make although your PCB is the gold coated, but you may think as it is the gold coated, it can be the highly expensive, but no. If you can make it in the large scale, you can reduce the cost. Although you may need the gold coat on the surface, but you are making like every day like million of chip in an industry level, then definitely the price will be reduced. But if you make only single chip, it may be the cost around maybe few thousand rupees, but you can reduce it just like the 50 to 100 rupees because you are fabricating this in a large scale. So this is the one important thing that PCB can be used for biosensor development. But when we receive the PCB from the industry, this surface is huge contamination there. I thought last few class the contamination effect, pretreatment methods. Let's use all the concept now for biosensor development. And for example, we are using the printed circuit board. So as I saying, it is the very ideal conditions. Let's show you first some PCBs. Like you can see, if you open the computers or the mobile phone, you can see this kind of electronic circuit. You can see that is all are on the substrate. Then we are using some PCB substrates, and those substrate, those PCB design you can use for sensor development. That I am going to tell you. You can see in the right hand side, I am showing one PCB. Here, see the channel. This is the simple microfluidic channel. Microfluidic channel. And you can see here this is the spot. This all the spot. This all the spot we can use as a electrode. So this PCB design we can easily PCB designer you can easily compose your own design. Like if you need something like this way or something like this way, or maybe you may need for multiplex detection like one chamber, one here, one here, one here. That also you can design. It's completely up to you. That's why you can play around the design here, and you can integrate this kind of microfluidics and there is a connector. You can use something like a connector, and you can insert your chip in that connector, and then you can apply all your like potential you may need to apply, or some current you may need to apply, that you can apply by using some potentiostat. Potentiostat that you can do. That's why we are saying the PCB is a very ideal condition, very ideal platform for biosensor development. But now I will show you few information here. When suppose this is an example of the printed circuit board, you can see like this is a multiplex printed circuit board, 1, 2, 3, 4, like 4 channel. So here maybe you can drop cast your antibodies, and one electrode, that is saying that your working electrode. This is your working electrode, and this one you can use the reference electrode, this one uses a counter electrode. Actually here we are using gold as a reference electrode. I think last class I taught you that generally we are using reference electrode silver coiled or calomel electrodes, something like this. But here, to make your chip very unique and to very user friendly and not to make very complications, we are using some noble metal as a reference electrode. Actually this kind of reference electrode is not much recommended, but still if you see the gold is a noble metal, they cannot be oxidized easily. So in this case this kind of electrode you can use as a reference electrode. But if you see any change time to time, it happen because of your noble metal, although you are using gold, then you have to think about the problem. Maybe this reference electrode somehow can be affected by your nearby some other, maybe below of this gold electrode you may have some other layer, copper layer also there. So it may be exposed. It can affect also the potential, that you have to keep in mind. That all the story I am going to show you in the next slide again, because you have in the case of the PCB electrode, first we are using a copper layer. On the copper layer we are using the gold. So if somehow during the pretreatment, during the cleaning, if somehow copper exposed, then it can affect on your data, because copper can easily oxidize, right? It can affect on the potential whatever you are applying. So let's see, when you receive this kind of PCB electrode from industry, from the fabrication, like where you can send your design, they can fabricate easily, and after that if you measure the cyclic voltammetry, so you can see here actually measure the cyclic voltammetry in a mixture of potassium. So we measure from left. Sorry, we measure from here, from right 0.3 to minus 0.3, means from first oxidation, then reduction, and it is that you have to use K3FeCN6, mean here iron 3 stage, right? Mean iron first reducing Fe3 to Fe2, then again oxidizing, right? See in this red one, the first one, this is the before cleaning. So when we didn't use any kind of pretreatment method, any cleaning method, you can see there is no peak almost. There is no iron Fe2, Fe3 reversible, this peak you cannot see, because your surface is too much contaminant when you receive from industry, from PCB factory. When they are fabricating the PCB, there is lots of contamination there. That's why I just wanted to show you here a AFM image of the printed circuit board that we received from the PCB factory. See immediately before cleaning, if we check, you can see almost the surface is covered by some contaminant. Here you can see that from the shape and from the electrochemical data, like two way, one is the AFM data and another is the electrochemical data. So these two data can help you to predict the surface impurities you have. Now you can go for some surface cleaning method, surface pretreatment method. What pretreatment we are following in this case? That I already taught you some different pretreatment methods. So, one pretreatment method you can follow like 15-minute ultrasonication in acetone, ethanol and water. So, first like very non-polar solvent like acetone, then you can go to little polar like ethanol, then polar water. You can sonicate it for 15 minutes, 15 minutes, 15 minutes, followed by you can make a mixture like 5:1:1 ratio like water, hydrogen peroxide and ammonium hydroxide. Then you can sonicate it, or even you can heat the solutions around 80 degrees Celsius and for like 1 hour. Then you can clean the surface with DI water and let us see the electrochemical behavior. See, immediately when you clean the surface, you can observe the reductions and oxidation, very good reversal peak. But at the very beginning there is almost no peak, only just a very small current you are getting, little bit current you are getting. But immediately after cleaning you are getting like this, very good shape, like Fe to Fe3 conversions happening now properly, this reversible reaction happening now on the surface properly. So, this information, that is why you should have whenever you receive this kind of PCB electrodes from PCB factory. Let us go for this kind of cleaning and let us remove all the organic stuff from on the surface. There is huge organic stuff on the surface. I will show you now XPS data. You can see how much contaminant there, and you can see this is the AFM image again. See, just after cleaning, surface you can almost exposed now. You can, and in the gold surface now, outer surface is the gold, but before that there is not much gold. That is why you can see almost no current and no peak. But when you clean the surface by this method, you can see the very good peak. This is very good information when you will use your PCB electrodes for biosensor development. Now, let us come the XPX study. Photoelectron spectroscopy study, you can see I mentioned no. So, BC means before cleaning, AC means just after cleaning. You see, just this is the gold peak, right? This gold peak very again the intensity was very low because it was covered by the contaminant. What contaminant? Organic contaminant. Then you can see the carbon peak here. See, before cleaning you have huge carbon peak. Why? Well, that is why you can see the AFM image is almost covered the organic contaminant. Okay, that you can clearly prove that here is a huge contaminant of the carbon material there. And you can see here for the before cleaning case, for the gold peak in the 4F region, it is very low. And when you go for the cleaning, you can see the very good peak you can observe, and you see almost after cleaning the carbon peak almost diminished, means almost there is no contaminant now and carbon almost removed from the surface. That is why you are getting very good reversible Fe2 Fe3 cyclic voltammetry here. So, like this way, whenever you want to develop the biosensor, let us characterize the surface very systematically. First go for the electrochemical measurement, then go for AFM measurement, XPS measurement, and you see the contamination. See the copper peak. One story I told you last time. When like PCB factory, they are designing based on your design, you send your design to the PCB factory, they use below a copper layer, and then on that copper they use the gold. So, if this copper is exposed during the pretreatment process, because very thin gold layer we are using on the top of the copper, few nanometer gold only. So, if somehow it exposed, it can impact the result. That is why, see, here you can see some copper peak actually after cleaning we are getting. So, before cleaning there is almost no copper peak, but after cleaning we are getting some copper peak. It means you have to think about which pretreatment method we will follow for your removal of the carbon contaminations on your PCB surface. I taught you many pretreatment methods, right? Now, you can link all the pretreatment method for this removal of the contamination of your transducer surface, right? That's why last few classes whatever I taught, they all are equally important for the development of the sensor surface, right? So you may use this very means a very strong cleaning method like piranha. You cannot use piranha because it can dissolve almost the gold from the upper surface, and copper can be exposed. And in this case you can see here we measure the peak with respect to gold reference electrode, right? Okay, I will show you very clearly now, because today I am showing you the another reference electrode for the PCB, right? Generally I was showing the reference electrode that is silver chloride, but here I am showing the reference electrode is the gold, but this is actually pseudo reference electrode, because this is not very much ideal. But if the potential is constant, means if there is no exposure of the copper can happen, then only it will be suitable. And you have to think about, there is gold dissolution should not be there. Suppose in this PCB surface you want to scan, like anodic treatment you want to use, right? Anodic treatment you can remember, like gold will be oxidized, then gold will be reduced, then like this, right? So maybe minus 0.2 to 1.4 volt, right? So gold can be oxidized means somehow gold oxide forming, right? AOX, gold oxide forming, and then that gold oxide again reducing. During this process, if the gold dissolve and copper can be exposed, it can affect on your sensor development, right? That's why you have to keep in mind that can we use this anodic treatment for this cleaning method of the gold PCB or not, that you have to keep in mind. Or if you can use, then how many cycles you can try, and what is the thickness of the gold, you should have all the information. Okay, this is very good means information for you for the PCB based biosensor development. Now let's come a PCB based biosensor development for glucose quantifications. So your sensor surface now clean, and it is ready for like some organic molecule immobilization. You can see this image, this is just bare PCB surface, this is bare after cleaning. So who is cleaning, that you have to decide, that I already taught you, and then you have to check which is the best cleaning method. So there should not be like this, too much copper exposure should not be happen, that you have to keep in mind. So after the cleaning, let's MPA, mercaptopropanoic acid. Why we use mercaptopropanoic acid for PCB biosensor fabrications? I think you can remember at the very beginning I taught you that gold and thiol, they have very strong interaction, right? Strong interaction. So if you drop your thiolated molecules on your gold surface, then it will easily bind. So mercaptopropanoic acid MPA is something like this is a linker that will help to bind some other receptor that you wanted to use on the PCB based biosensor. So this is your PCB based biosensor. We just drop casted your mercaptopropanoic acid, then we wash the surface, then we got this carboxylic acid group on the sensor surface. So mercaptopropanoic acid, it has a functional group. This functional group is COOH. So this is a very important functional group for biosensor development, you know, COOH or maybe amine group you can functionalize. So in this case we tried carboxylic group and we use MPA. You can remember, if you have the carboxylic group on your surface, then you can try EDC-NHS activations process, right? EDC-NHS, that you can remember that I think you know that for the glucose quantifications we want to modify on the sensor surface glucose oxidase. So glucose oxidase enzyme, it will selectively oxidize the glucose. So this is a enzymatic biosensor, but here we are using some process of the modifications for MPA for carboxylic group. First you brought the carboxylic group on the sensor surface, then you activated this carboxylic group with EDCNHs, because this is just a catalyst. It can activate this carboxylic group. See, glucose oxidase, it has the amine group, free amine group. So carboxylic group, amine group, they can bind, they can form amide bond, but they are thermodynamically they are fine, they can react, but kinetically they are very, very slow. So how you can make faster reaction? For that you need EDCNHs. So they will activate the carboxylic group, and then this glucose oxidase will bind on the sensor surface. This activated carboxylic group will react with the amine group, or you can say the amine group will react with this activated carboxylic group, and then glucose oxidase will be attached on your sensor surface. So your sensor surface now ready for glucose detection. But you have to keep in mind, as you know, now slowly you become the expert of the sensor development of the surface. So you may need many times the washing of the sensor surface. So you have to be very much careful of the washing of each step. Like after the cleaning, definitely you have to go first thoroughly wash your surface. If there is some contaminant present, it may impact on your sensor reproducibility. So after treatment, very you have to be careful the washing steps. Thoroughly clean and then dry the surface with some nitrogen gas. You can dry with some nitrogen flow, you can flow the nitrogen, then dry it, then use this MPA. Then again after the modifications of the MPA, this is the organic molecules, then you may need the ethanol here. So ethanol solution, after the modification, then again wash it thoroughly, then dry it, and then again you can dip this surface in the EDCNHs solution. After that you have to clean it properly. There should not be any unbound any other molecule, otherwise when you add the glucose oxidase, they may bind with the other unbound molecules, or maybe some unbound stuff there, they can bind. So you have to be very careful for the washing step during the modifications of the biosensor surface. Okay, so this biosensor now ready for glucose detections. And why we choose the glucose oxidase? Because glucose oxidase is very specific for the glucose. Later I will teach you, without glucose oxidase also we can modify the sensor with some nanoparticle, because if we can develop very specific nanoparticle that can oxidize specifically glucose, it also has impact, because there is some drawback of the glucose oxidase because it is a protein. You cannot store longer time in the room temperature, right? So that's why if you want to really wanted to form a point of care device, you have to think about extreme conditions, like at the very high temperature in the rural conditions. If you want to store your electrode surface, then there may not be available, and refrigerator not available, right? So how will you store this at the 45 degrees Celsius in the summer time in the rural area? That time this kind of enzyme may be denatured easily. So you have to think about, one, maybe you have to stabilize the surface anyhow, otherwise go for some non-enzymatic process. That is the drawback. But what is the advantage of the glucose oxidase? Advantage, although they are protein, they are very specific for the glucose. That is the advantage. So enzyme assisted glucose now quantifications, you can see this. This is a chronoamphogram, chronoamphometric study we did, and you see different concentration like the zero data. So what is your zero data? Means this is the surface for the zero data. So you can drop here just your without glucose solution you can add, and then you will see like this blue one. This is the zero data. Now slowly increase like 10 micromolar, 100 micromolar, 50, 1 millimolar, 3 millimolar, 9 millimolar. We are increasing the concentration, and current also can be increased on your sensor surface. Okay, so enzyme that already mobilized on your PCB surface, now it is showing the oxidations of glucose, and you can, like I already taught you, this is a calibration curve, how to develop, how to make a calibration curve, that you know. So maybe you have to fix a time, the suppose 10 seconds. In this time you can measure all the current for each concentration, and for each concentration you have to measure 3 concentrations. See, this is the error bar for 3 data, and for each concentration we just put all the current for the different concentration, and this is the different concentration of the glucose in the x axis, y axis is the current. And why I am saying here corrected current? Corrected current because we are subtracting the zero data from the, see, suppose you are getting this much zero data, right, and your 10 micromolar data is this much. So if you subtract the zero current from the 10 micromolar current, then actually how much current you are getting for the 10 micromolar, that you can get that corrected current I have shown you here. That all the corrected current for the all the concentrations we plot it, and then we got the calibration curve. So your PCB now is ready for the glucose quantification. So this is really important biosensor for especially where we can use this PCB based glucose sensor. One is painless lab on a chip patch, that I wanted to show you these applications. Now slowly I am entering again, use this kind of biosensor for extreme point of care or develop some biosensor device. So now we are looking for some biosensor device, so that this after pretreatment, after cleaning, your PCB sensor ready for glucose quantifications. Now let's use for some patch development. You can see on this PCB we immobilize the glucose oxygen on the working electrode. We can integrate some microfluidics, and from here you can pass your real sample, like if you want to use the sweat sample, or maybe if you want to use some serum sample, that you can pass. And then like here you can see one inlet, one outlet. I mean, we can make a device. I mean, this is just the laboratory setup. Maybe next class I will show you the actual patch, how it looks like. But first let's develop the prototype concept in the laboratory based. Let's try to learn how we are developing the prototype in the laboratory conditions, and then use that prototype for actual patch that you can commercialize. This part you cannot commercialize. This is just for the laboratory setup. Very miniature chip we develop using the PCB. Now let's use the inlet on outlet. In the inlet, like a artificial sweat you can make, and that artificial sweat let's pass through. Then outlet, from there your all excess artificial sweat can pass out, and then you can check their concentrations of the different glucose. Then similar kind of data you may get in this setup also. It means your PCB setup is ready for patch development. A painless patch, why I said? Because here I wanted to use sweat sample. And one important thing you have observed here, see, 10 micromolar glucose we can detect from this setup, and our sweat glucose level is really very low, but your serum or blood glucose is very high, millimolar range, but your sweat glucose level is micromolar range, and your sensor can detect in the micromolar range. So this sensor can be useful for painless lab on a PCB patch implementations. That's why. So now these whole systems, in the next class I will show you a very small patch we can develop just like a band-aid, and we can put on your screen, on your skin, and then you can measure the concentrations of glucose on like in your sweat sample, and using your IoT concept, I mean Internet of Things, IoT concept, you can transfer this data to your mobile phone also. That all the advantage, disadvantage, and still you have we have some other mechanism for this patch development that I will teach you in the next class. So you just keep in mind when you develop some kind of patch sensor or any real sample based biosensor, you have to think about interference study. Because with the real sample you may have fructose, uric acid, ascorbic acid with glucose. You are detecting glucose, but you may have some other interference species. They should not show much background current, right? That's why we measure some other also. See, so your glucose is here, but your fructose, your uric acid, ascorbic acid, others, they are not showing much background current. So your sensor, that's why ready for glucose detection, because in this real sample not much interference effect present. Okay, so that's all for today's. But next class I will take a tutorial also. I will give you some problem, and I will discuss this all the tutorial problems how we can solve. So one by one I will tell you how to solve this problem, and I will discuss, and also next class I will discuss the patch development, and then I will come to the next some wearable biosensor device development. So this patch kind of biosensor is a wearable sensor. So this concept I just started today, then I will cover next class. Also I will discuss some problems so that you can design your own biosensor, like this like 6 problems I just made, that I will discuss one by one all the problems, and then finally I will go to the another biosensor, that is wearable biosensor for other analyte detection. This wearable sensor that I started today, that is glucose detection using some wearable patch. So today's main conclusion, just try to learn that is the pretreatment procedure is very important for biosensor development, because it can remove all the contaminations. Although it can remove the contaminations, like which pretreatment is the best for biosensor development, for which substrate, and then modify like your common substrate for biosensor development, and use some really important target detection, because right now we have glucometer, but we need blood samples. But today I started like how we can develop a glucometer type of sensor from the sweat sample. Okay, that's all for today. Thank you very much.